a profoundly important announcement to make, which is the most epic chip-building exercise in history by far. We aspire to be a galactic civilization. So I think the future that everyone, well, most people, I think, would agree is the most exciting is one where we are out there among the stars, where we are not forever confined to one planet, that we become a multi-planet species, like the best science fiction that you've ever read. You know, Star Trek, or Ian Banks, or Asimov, or Heinlein. And we want to make that real. Yeah, we want to be a civilization that expands to the galaxy with spaceships that anyone can go anywhere they want at any time. That would be epic. And have a city on the moon, cities on Mars, populate the solar system, and send spaceships to other star systems. That sounds like the best possible future. You know? So to do that, we need to harness the power of the sun. So to accomplish this very difficult goal really requires a combination of efforts of SpaceX, XAI, and Tesla working together to create this epic TeraFab project. So this gives you sort of just a sense of scale. We've got Optimus there, Optimus for scale. And Optimus is about 5'11", so it gives you a sense of the size of the Starship V3 rocket. Starship V4 will be much longer, actually. The Starship V4 will make Starship V3 look kind of short. So we'll expand with Starship V3 to 200 tons of payload to orbit, from 100 tons with V3. And then you can see that that's just a rough approximation of the mini version of the AI sat. So that's roughly 100 kilowatts. It's showing the solar panels and the radiator to scale. So in order to get to the terawatt of compute per year, you need about 10 million tons to orbit per year, and at 100 kilowatts per ton. So, but we're confident this is feasible. Like no new physics or impossible things are required to get there. So I'm confident actually that SpaceX will get to 10 million tons to orbit per year. And then we're building up to a terawatt of solar. So that will solve the solar problem, the power generation. So then the key missing ingredient is therefore a terawatt of compute. So this announcement is about solving the key missing ingredient. To give you a sense of what we're talking about, the current output of AI compute is roughly 20 gigawatts per year. So if you add up all the fabs on Earth combined, they're only about 2% of what we need for the terawatt project, or TeraFab project. And we're starting off with an advanced technology fab here in Austin. So in the advanced technology fab, we will have all of the equipment necessary to make a chip of any kind, logic or memory, and we will also have all of the equipment necessary to make the lithography masks. So in a single building, we can create a lithography mask, make the chip, test the chip, make another mask, and have an incredibly fast recursive loop for improving the chip design. So, and we're not just going to do conventional compute in this. I think there's some very interesting new physics that is potentially, that actually I'm confident will work. It's just a question of when. So this is we're really going to push the limit of physics in compute. And we're going to try a bunch of wild and crazy things, which you can do if you've got that fast iteration loop. So broadly speaking, we expect to make two kinds of chips. One will be optimized for edge inference. So that'll be used primarily in Optimus and in the cars, but especially in Optimus, because I expect the robots, humanoid robots, to be made 10 to 100 times more than the volume of cars. So, you know, if vehicle production on Earth is about 100 million vehicles a year, and I expect humanoid robot production to be somewhere between 1 billion and 10 billion units a year. And then we need a high-power chip that is designed for space, that takes into account the more difficult environment in space, where you've got high power, you've got high energy ions, photons, you've got electron buildup. It's a hostile environment in space. So you want to design the chip, you want to optimize it for space. For the space compute, my guess is that is the vast majority of the compute, because you're power constrained on Earth. That's why I think it's probably 100 to 200 gigawatts a year of terrestrial chips, and probably on the order of 1 terawatt of chips in space. The cost of AI and deploying AI in space will drop below the cost of terrestrial AI much sooner than most people expect. I think it may be only 2 or 3 years before it is actually lower cost to send AI chips to space than it is on the ground. Because in space, you don't need much in the way of batteries, because of it's always sunny. And the solar power, you're going to get at least 5 or more times the solar power you get in space versus the ground. As soon as the cost to orbit drops to a low number, it immediately makes extremely compelling sense to put AI in space. And you get there by having an electromagnetic mass driver on the moon with robots, with Optimi, and obviously lots of humans. And with that, you can send a petawatt. You can create a petawatt of compute and send that to deep space. Because on the moon has no atmosphere and has 1/6 Earth gravity. So you don't need rockets on the moon. You can literally accelerate it to escape velocity from the surface. And that dramatically drops the cost, once again, of harnessing power and enables you to go 1,000 times bigger than 1 terawatt. Obviously, the elements of that are sustainable energy, space travel, and AI and robotics that bring amazing abundance to everyone. And then we go beyond the moon, beyond Mars, and we sail through the rings of Saturn. Now, wouldn't it be amazing if you could buy a trip to Saturn? Or frankly, if you just have a trip to Saturn, I think things will just be free in the future. And help us design incredible chips and make incredible chips and build 1 terawatt of chips, 1 terawatt of solar, and 10 million tons to orbit per year. Thank you.